This video continues the discussion of atmospheric water vapor. Specifically, we'll discuss how atmospheric water vapor is quantified and measured in the atmosphere. To do so, we'll introduce partial theory. Partial theory assumes that the atmosphere can be divided into small, isolated volumes or masses of air. This would be illustrated by this little cube at the bottom of this figure over here. This parcel stands in contrast with this column of air here, column B. A column of air extends from the surface of the Earth all the way up to the top of the atmosphere, whereas a parcel is much more limited in its reach. This parcel in particular is in contact with the surface of the Earth, and that is an assumption we'll make for all the air parcels in this particular section. If we look at this at a microscopic level or at a molecular level, that would be illustrated in this figure over here. You'll notice that within this parcel there are dry air molecules represented by the yellow, and blue. These blue little spheres represent water molecules. This is water in vapor form. In the ocean or in the water below, this represents liquid water, and these molecules are in their liquid state. Note that we are in vapor equilibrium, which means that the amount of evaporation into the parcel equals the amount of condensation and precipitation out of the air parcel. So how to quantify the amount of water vapor molecules in the air parcel? Well, we have three ways of doing that here: mixing ratio, specific humidity, and vapor pressure. Mixing ratio looks at the mass of water vapor in grams and compares it to the mass of dry air. That is to say, the mass of oxygen and nitrogen atoms in the air parcel. Typical values of this are 1 gram per kilogram, meaning that the number of water vapor molecules in the atmosphere is typically 1/1000th of that there is in terms of dry air. A very similar quantity is specific humidity, which looks at the mass of water vapor and compares it to the total mass of air in the air parcel. So the difference here being that the total mass actually includes the mass of the water vapor. So you're adding together the mass of the water vapor molecules and the mass of the dry air to measure this kilogram of air. The final quantity is vapor pressure. Now recall that the total pressure represents the force that these molecules exert when they collide with the surface of the Earth. The vapor pressure is the total pressure exerted by only the water vapor molecules. Okay, so that value again is typically about 1/1000th of the total pressure of the atmosphere. But essentially, these three all measure the same thing. They measure how much water vapor is in the parcel of air that you are measuring. So instead of looking at air parcels, in the next portion of the video, we'll examine the entire column of air to see how much water vapor is in it. To do so, you have to take into account that water vapor is a greenhouse gas, and that it will, in other words, that it will absorb infrared radiation as it goes through the atmosphere. So this chart that you see here looks at the absorptivity of the atmosphere towards different amounts of different types of electromagnetic radiation. This shows the absorption in percent, which extends from 100% to 0%. So for example, in the visible part of the spectrum here, indicated by this range over here, the absorptivity is 0%. So water vapor just lets all the visible visible light go out into outer space when it strikes it. However, for infrared radiation, it can absorb quite a bit. In this range over here, a wavelength of about 5 micrometers, it absorbs almost everything. We move on to the IR3 band of infrared radiation between approximately 13 and 14 micrometers. If you'll notice in this band, about 50% of the infrared radiation that passes through the atmosphere is absorbed. That makes the IR3 band ideal for satellite measurements of water vapor in the atmosphere. This is what a satellite measurement of water vapor in the atmosphere looks like. This is actually a storm system that's rotating in this direction. That's why the water vapor is sort of going in a swirly pattern. Areas that are milky, like over here and over here, represent areas with large amounts of water vapor. Darker areas over here represent areas with very little water vapor or relatively dry air. This little slot of dry air is actually called a dry slot, which is typically associated with storms. Ahead of the dry slot is actually a moisture plume or an atmospheric river extending from the Gulf of Mexico all the way to the eastern coast, northeastern coast of the US. The brightness here indicates not only the presence of water vapor, but where it's totally white actually represents the presence of cloud and probably precipitation as well. But overall, what you see in this map is where there is dry air and where there is humid air. Another quantity that can be used to measure the amount of water vapor in an air column is something called precipitable water. Precipitable water is measured in millimeters or inches and gives you the potential amount of rain that can fall in a given region. So you'll notice areas in red are around measure about 50 millimeters of precipitable water. 50 millimeters represents approximately 2 inches of potential precipitation. And you'll note that the tropical air mass here in red gives you a very large 2-inch potential for precipitation. In the meantime, these areas here in gray around the high pressure system over here represent areas with less than 10 millimeters of precipitable water. This means that the likelihood of precipitation in this area is very small, and if it does precipitate, that the amounts will actually be relatively small. We click on a current map of precipitable water for August 3rd. This actually represents a 3-hour forecast valid at 15Z on Monday, August 3rd, 2015. On the left, we see precipitable water, and on the right, the map represents the predicted amount of precipitation that will fall in 3 hours. All of this is measured in millimeters. This is actually associated with the front that is forecast to move through Monday afternoon on August 3rd. You can see this elongated frontal structure of high values of precipitable water, and that is associated with these high values of 3-hour precipitation. Notice that not all the precipitation shown here is actually going to fall. You can see these amounts hover around 30 or 50 millimeters, whereas over here the precipitation amounts are between 2 and 5 millimeters. So precipitable water should always be seen as sort of the maximum potential precipitation in a given weather system.